Good morning, guys. It's me again. We're back into our dynamic of A-level chemistry. It's the second chapter of Cambridge A-level chemistry. It's chapter 20, Electrochemistry. And the reason why I'm not uploading the chapter 19 is that I made a stupid mistake yesterday. You see, I got all my notes here. I recorded this, explained everything, but I just forgot to turn on my microphone, so let's just forget it. Yeah, maybe I'll do it again sometime. Okay, let's forget this unpleasant memory. So today we are gonna to explain you about electrochemistry, about those redox reaction, electrode potential, and electrolysis. What is essential in A-level chemistry, and it is essential in chemical industry. So we are gonna start with our first part. We'll start nice and easy. Electrolysis. Electrolysis. First, we have to talk about definition of electrolysis. Lysis is the word, means breaking down in Latin, and electro is just electricity. So the definition is the decomposition of a compound into its element by electric current. We will explain further later, so I'll just write it here. And I actually found some very beautiful graphs for this. So for example, this is a good graph here. Paste here. This is just a brief illustration for electrolysis, the device, the apparatus we used for electrolysis. Here it's a negative electrode, although known as the cathode. And here is the anode. So what's important is that in anode, oxidation happens. Oxidation happens, and at cathode, reduction of anion happens. Also, just for you to memorize, cations goes to cathode, and anions goes to anode. I'm sorry. This is just a brief illustration of our apparatus for electrolysis. A good example will be the electrolysis of zinc chloride. We can know this is zinc chloride. It is a solid. Yeah, it is solid, but if we want to electrolyze it, we have to dissolve it to form electrolyte. Electrolyte is what we decompose by electric current. You can hear my voice is a little bit lackluster because I went to bed at 3 a.m. yesterday, and actually today, yeah. So I'm still half asleep. Okay. The net effect of electrolysis of zinc chloride is we form solid zinc and gaseous chloride as our product. But what's the process? The process is zinc 2 plus cation in aqueous solution. It gains 2 electrons, so it forms zinc in solid state. And two chlorine anions just each gain 1 electron, so it forms chlorine molecule in gaseous state. See, they're all in their basic state. They're all in their natural state, and those elements are broken down by electric current. You see, we got direct current power supply here. So yeah, that's just a brief introduction for electrolysis. Now we are gonna have a closer look at the process. So first, what we are gonna do is to turn it to quantitative, I'm sorry, my pronunciation. Quantitative electrolysis. We need to know when a certain current is applied for a certain period of time. We want to know how many moles or how many mass of the product in each pole of that apparatus we're going to obtain. Now I'm going to introduce you a very important quantity called Faraday. It's actually a unit. The symbol for Faraday is F, of course, capital F. So what's the definition? 1 Faraday is the quantity of electric charge carrier by 1 mole of electrons, or singly charged ions like chlorine minus, like protons. So what are we going to do with this? As I presume that you have all the knowledge from AS level physics, I'll just write this formula down. Here you see what's Q. Q is charge, and I is of course current. T is time. Charge equals to current multiplies time. The unit for Q is C, and the unit for I is A, ampere. I'll give you an estimation for 1F. 1F equals to 96,500 coulombs per mole. That's an essential data. So later we'll use this frequently, and you'll see how we are going to apply it on our problems and to solve things. For example, if we are going to reduce silver plus to silver solid to its ground state, to its natural state, 1 electron is required for each molecule of each cation actually. So if we want to obtain 1 mole of silver solid, we need 1 mole of silver cation and 1 mole of electron. And the charge by 1 mole of electron is equals to 1 Faraday, which is also 96,500 coulomb. So what's the point? To make things easier, we'll break down this to a simple problem. If we got an electric current of 1.50 ampere and it flows through molten PbBr2, which is lead bromide, for 20 minutes. Of course, 20 minutes is 1,200 seconds. That's basic knowledge. So what are we going to do first? First the question is, what's the mass of Pb produced? Okay, what we're going to do first, step 1 is we write down the equation, how the oxidation or reduction reaction happens. Do it like this. So you see we need 2 moles of electrons to reduce 1 mole of lead 2+. And here we need to calculate how many, step 1. So step 2, we want to calculate how many charge do we have in 20 minutes. Recall that Q equals to IT, so Q equals to 1.50 times 1,200 seconds, which equals to 1,800 coulomb. We know that 1 mole of electrons is equals to 96,500 coulomb. So how many electrons is there? How many electrons are there? We just use a fraction to evaluate it. And you can see we need 2 moles of electrons to reduce 1 mole of Pb2+. So we times half and equivalence. And here we put all of these values in our calculator and get, wait a second. And we will get 9.33, I'm sorry, times 10 to the power of minus 3 moles of Pb2+ is reduced. And as the amount of Pb produced and Pb2+ are equal, so we can easily get the mass of Pb, which is equals to relative mass of Pb, which is 207. You're welcome. Times numbers of mole times the amount. So we do it like this. And we got 1.93 grams. This is the final answer. So we see this is just a simple application of Faraday and the formula Q equals to I times T. It is basic. It is based on our general knowledge for electricity, charge, and chemistry. Yeah, it's just basic chemistry. So another good question is, at room temperature and pressure, the current of 0.50 ampere is flowed into concentrated sulfuric acid, and time equals to 30 minutes. First, we need to figure out what's the formula of this reduction or oxidation reaction. First, if you see concentrated sulfuric acid or aqueous sodium sulfate. You all know that the equation should be here 4 hydroxide produce 2H2O plus, don't forget state symbols, and 4 electrons. Here, state symbols. This is important. Yeah, here. I don't want to lose mark because of this, so be cautious. Sometimes you have to be caustic at yourself, right? So first, as usual, we just calculate the charge, which equals to 0.50 ampere times 1,800 seconds, which is 900 coulomb. And here you see 4 moles of electrons is produced when 1 mole of oxygen gas is produced. So the number of oxygen should be a quarter of the number of electrons, which is 1/4 times 900 over 1 Faraday. So let's let's obtain this value. 900. This is 2.33 times 10 to the power of -3 to be clear. Always use 3 significant figures because it's safer. And at room temperature and pressure, now we can calculate the volume of oxygen. We know that 1 mole of ideal gas occupies 24 decimeter cubic of volume, and so we just use 24 times n, and we get 5.60 times 10 to the power of -2 decimeter cubic. Yeah, this is the final answer. So you see, that's pretty simple. It's just basic calculation based on this new knowledge about electrolysis. Now we are turning to 20.3, section 20.3. We're going to talk about electrode potentials here. Maybe you ask, how can we ensure this reaction will happen, or in which direction it will happen? For example, this reaction with the electrolysis of concentrated sulfuric acid. Why can't it happen in reverse direction, or why it happens? Yeah, this is actually a good question, and this makes scientists confused for decades. And now we got answer: electrode potential. First, we still have to define this definition. It's the potential difference between a metal ion system. Just want to make sure that I open up my microphone. Yeah, I think so. Yeah. Perfect. System and another system. Here I got a good example for you. I got a beautiful graph here, and I suppose we'll use this for several times. I'll show you now. Here you see on the left hand side we got a copper 2+ ion system, and on the right hand side we got a zinc 2+ ion system. So what's this voltmeter measuring is the potential difference, the electrode potential. So that's really perceptive sorry, my bad. Perceivable, that's pretty straightforward. And what's the next? Yes, and look, in general, in practice, we cannot directly measure the potential difference of one half cell, isn't it? Because we don't have a reference. So a good reference will be standard hydrogen electrode. Its apparatus look like this. I'll draw this. I'll try. Like this. Okay. And we got a beaker for that. Yeah, I know this is absurd, but anyway, we can use that. Here is platinum electrode. Platinum is a very inert substance, so we just make sure it doesn't react with hydrogen or water inside of here. And here is 1 m of proton solution. And here we have a constant supply of hydrogen at 180 m atmospheric pressure. And this is just a pore for hydrogen gas to live. Hydrogen bubbles, to be honest, to be more clear. To leave. Okay, what's happening in this half cell is the reaction down here. And in later discussion, we'll see the E standard for this is 0.00 volt. And this is our reference because we use this as 0. So if we connect copper 2+ system with our standard hydrogen electrode, we'll get the standard electrode potential for copper 2+ system. Here, now we'll see what's the point. What's the point of electrode potential? I'll open up my fans. It's too hot in Zagreb here. It's almost summertime here and we don't have air conditioner in our apartment, so I don't know why. I don't think they won't need that. Anyway, let's continue with this. So as we are naming this as potential, it shows some tendency of reaction. So if we get a more positive E, more positive electrode potential value, is more feasible for forward reaction. A good example will be Ag plus Aq plus electron, and it produced silver solid. E standard equals to positive 0.80 volts. So which means producing silver solid is more feasible, is more favored compared to generating those charged ions, charged particles. Here, it's just a reverse statement. So maybe you can know that if electrode potential gets more negative, it's more difficult to reduce ions. On the left. No. It's first more feasible on reverse reaction. A good example will be zinc. Zinc 2 plus aqueous plus 2E. We got zinc solid, and the standard electrode potential equals to minus 0.76 volts, which means it's not feasible to generate zinc solid. Okay, and as we got statement here, see, it says more feasible on reverse reaction or more feasible for forward reaction. We know that the forward reaction is always reduction, which means if E is positive, it's easier to reduce ions on the left. Vice versa, if E is negative, it's more difficult to reduce ions on the left. I'll explain further in my Housecroft, I think chapter 9 lecturing. So we'll be able to practice more qualitative and quantitative discussions, like using some more advanced formulas and expressions. But now for A level, this is good. This is perfect. Now, yeah, you probably heard that I'm saying the word half cell. What's a half cell? What's a half cell? Half cell is something like that. I'm too lazy to draw my abstract diagram. Oh no. Oh, I don't have screenshot for this, so I'll show you this. For example, just assume this is a copper rod. I know this is absurd, and this is ugly. CuS, it is pure. It has to be pure. And we put it in a beaker. In this beaker, it's 1 mole of copper 2 plus solution, 1 m concentration. So, and now the temperature equals to 25 Celsius degrees, or T equals 298 kelvins. It's just room temperature, isn't it? So when we are connecting two half cells, how are we going to connect this? Here, yeah, fortunately I got a graph here. Yeah, we can use the same graph actually. We can use the same one. You see, on the left-hand side, this is the half cell I just drew seconds ago, and we connect two of those half cells by a wire here. This allows exchange of electrons. And here a salt bridge. A salt bridge can be made of filtering paper soaked with saturated potassium nitrate solutions. This is just a porous. This is just a porous intermediate that allows exchange of ions. But not electrons. This is essential here. Yeah. Okay. So what's the net reaction of this half cell? The net reaction is you got copper 2 plus zinc, and you got zinc 2 plus and copper solid. Don't forget state symbols. You'll lose marks for that. And how do we know this? Recall the electrode potential definition. How do you know? Oh my God, I'm sorry. How do you know this? First, I will give you two formulas. Cu2 plus 2E equals to Cus equals to plus 0.34 volts, and zinc 2 plus 2E equals to zinc solid. E standard is minus 0.76 volts. So as previous knowledge, we can know that E standard for copper is positive. So it's more, so the forward reaction is more favored. And as it's minus for zinc, the reverse reaction is more favored. So we can obtain an expression like this. As the electrons just got cancelled. So like this. And what's the E standard of this cell? You know, if we call something like this a half cell, then two of this, we call it a cell. And that's purely logic. And we got 0. minus, we got 1.10 volts. This is how we calculate the potential difference of an electrochemical cells. So I will just label this electrochemical cells. Okay, perfect. So we were always referring to standard electrode potential. This. What's the factors? What's the conditions of this? First, concentration of any ions has to be 1 mole per decibel cubic, and temperature is 25 degrees. Any gas P equals to, or just 100, 1 kPa is fine. Or 1 atm. Both of that are perfect. And any values of any value, single form, electrode potentials. Must be measured with standard hydrogen electrode. As we're calling it standard, we're using this as a reference. So we can obtain a definition for this. The definition is the voltage measured on the standard conditions. With standard, not stand, oh, spelling, standard hydrogen electrode as another half cell. Keywords are on the standard condition and with standard hydrogen electrode. These are key points if you are getting question about the definition of standard electrode potential for 2 marks. There will be 1 mark for this and another mark for this. So that's really essential. Just memorize this. There's no other way to do this, to do it. Okay. Now we're turning to 20.4. How can we measure standard electrode potentials? Measurement. That's actually pretty easy, but we have to discuss in 3 different situations. First, a metal ion system. Second, non-metal ion system. And third, it's what's the third? Ions of same element in different oxidation state. Okay, we are doing it part by part. All of us know that how to measure the first one. The key point is you use a platinum electrode. We always use platinum electrode because it's more stable, it's more inert. And for the second one, here I got a very good example. Oh no, I'm sorry. Chlorine gas plus 2E 2CO minus AQ, and we just do it like how we assemble the standard hydrogen electrode like this. Here is the platinum. Here we got liquid, and the concentration of Cl minus 1 equals to 1 mole, 1 m. Here, pressure of Cl2, it must be 1 atm. And we just connect this with a standard hydrogen electrode. That's actually pretty simple. And this is substances in gaseous state, and how we measure a substance in solid state, which will not dissolve. A good example would be sulfur. For sulfur, we just do it like this. It's the equation should look like this, and And we also have, here is also platinum electrode. No. Here is sulfur. Here is sulfur 2 minus solution, which is also 1.00 mole per decimeter cubic. And of course, platinum electrode. That's basically it. And for 3, I would say a good example will be Fe3 plus E minus to Fe2 plus. This is basically the same as our previous discussions, and here it should be also platinum electrode here, and here Fe3 plus and Fe2 plus equals 2. So an equilibrium can be reached as soon as possible. So that's basically 20.4, and we are turning to 20.5. 20.5 is about the applications of E standard values. Applications. First, the most common application is calculate E standard cell. E standard cell equals to E standard, the more positive E standard minus the less positive E standard. Less positive. For example, a good example will be still silver and zinc. I'll just skip all of those state symbols, but I would say it's crucial to write it in real exams. Oh, no, I will not skip it. I won't. If you are skipping this in real exams, you are losing significant amount of marks. So we can see it's obviously this is more negative, this is less positive, or so we just do it like this, and we got this. What's the net reaction of this? It's this is the net reaction. You see, because the silver reaction goes into forward direction, and the zinc goes in reverse direction. That's pretty perceivable. That's simple, I would say. That's really simple. And we're turning to our second application. Here we can use this to determine direction of E flow. Okay, I will give you another graph I prepared. Do I have it? No. Yes. Got it here. Paste. Okay. So you see we got 2 half cells and we connect it successfully like this. shouldn't write it here. There are not enough. There's no enough space for me to write. So, all of us know that the direction should go like this. So, copper is reduced. And from previous knowledge, recall from previous knowledge, we know the one got reduced is cathode. So here is cathode here. And then the another has to be anode. And you can see here, copper is where the electron is accepted, and hydrogen is where the electrons are donated. So, the electron flow looks like this, from hydrogen to copper. That's easy, right? That's easy, isn't it? So we're gonna just skip this small part. I'll put it here, if just in case anyone want my note. It's clear. Oh my god, oh my god. Oh gosh. That's not clear at all. That's not clear. I'll fix it, don't worry. Okay, now let's turn to the third application. If we say that electrode potential contains information about tendency of this reaction, of this equilibrium, this reaction in equilibrium, so we can use the value to predict if a reaction will happen. So, more positive. E cell. Easy to not sell when we are talking about reduce, right? So it's easier to reduce. And more forward. Favored. Vice versa, that's omissible here. So I'll just skip it. Wings VV. I don't know if it's correct abbreviations. Abbreviations. Yeah, abbreviation. That's the real way to pronounce this. So we can know that if we got a higher E standard, it's very easy to reduce, which means it's a very strong oxidizing agent. If it's lower, it's stronger reducing agent because it's harder to reduce. I'll provide a further illustration for this in the courses for Housecroft in organic chemistry. That's university level of organic chemistry, so we can do a further discussion and more detailed discussion about this. Oh, I love honey water. There is actually a word in Japanese called hajimi for honey water. But you know, Chinese people around me are just misunderstanding hajimi as kitties. I don't know. They're having fun saying that every day. Hajimi, hajimi, hajimi. Like this. Okay. enough gossip. So another very good example will be zinc and copper. I know I've used that for several times, for like 10,000 times today, but it is a good example. It is good example. 0.76, I believe, and this. So if we connect these two half cells, we can clearly know that the direction should be like this, should go like this. So we can know the reaction that will happen is zinc plus copper 2 plus. It turns to zinc 2 plus copper. But this reaction, it will not happen. This never happens. This, oh, wow. And this happens. Another explanation will be that as zinc 2 plus is more negative, has more negative E standard, it's a stronger reducing agent compared to Cu2 plus. So it cannot get reduced by copper. So the lower this reaction, it won't happen. So this is pretty easy, right? And you may now ask, for the previous like 50 or 40 minutes, we were constantly discussing this electrode potential with standard conditions. What will happen if it's not standard? What's happening if concentration changed? Concentration changes. What will happen if concentration changes? First, recall that Le Chandelier's rule, the Chandelier's principle. For example, we also got this, we also have this formula as our example. If the concentration of zinc 2 plus increases, the reaction has tendency to move more forward because it shows more tendency to produce more zinc to use up or the excess zinc 2 plus. So we can know that if it's going more forward, we can know from knowledge of here. If it's more forward, it's more positive. So E standard is higher than minus 0.76 volts. Yeah, and now we are gonna to get a more advanced equation of that. It is the Nernst equation. You may ask, what will happen if we don't only change solution, if we change temperature or something? What will happen? So Nernst equation is that the equation. You can put everything inside of it. You can plug all those values inside and you can obtain the accurate value of the electrode potential after changing standard conditions. E equals to E standard plus RT over ZF. I will explain these quantities one by one later. Ln over oxidized form and Ln above and reduced form. So a good example will be, again, this equation here. See, what's the oxidized form? This is oxidized. Copper is oxidized. Wait a second. No. Here. Look. Copper is reduced. Yeah, copper is reduced because it is produced. It's reduced from copper 2 plus, and copper 2 plus is oxidized from copper. So oxidized form is copper 2 plus and reduced form is copper. And what's Z? Z is the number of electron transferred. It's 2. In this case, it's 2. And of course, T is temperature in kelvins. Of course, in kelvins, absolute temperature. So we can clearly know how this equation works. And when you get a temperature, a formula, and concentration of these two oxidized form and reduced form, you can just plug those values in and obtain E value on the non-standard conditions. However, we have a simplified form for this. This is only for metal ion electrode. E equals to E standard plus 0058 over Z log 10 concentration of oxidized form. The reason why we are not considering the reduced form is that reduced form is the metallic substance, is the metallic solid. It doesn't have to get a value for concentration, so it will be easier if we just use this. But if T is not 298 kelvins, use Fornernst equation. Okay, that's basically it. And now the most demanding part for both of us has finished. And we are turning to session 20.6, batteries and cells. This is just an easy chapter. I'll just put some of these graphs here and you can see. Cut. Paste. Here. This is lead acid battery. This is a secondary battery, which means it's rechargeable, and each lead plate provide 2 voltage each. 2. And we just connect 6 of those, so it can provide a 12 voltage of potential difference to light up the car and to start the car engine. And here is the fuel engine. It's the hydrogen fuel engine here. It is more advanced engine, more eco-friendly engine. No. I'm got confused. I'm a little bit sleepy now. Fuel battery, or fuel cells. The definition for fuel cells is where fuel and oxygen reacts, produce potential difference. It's more eco-friendly and is a further application of hydrogen. Is a more advanced invention. So hydrogen enters by here and oxygen enters by here. The product will leave as water here. Here are two porous electrode coated with platinum for these two to react, and the general equation is just a very simple one, like this. Like this. The advantage is water is only produced, so there's no harmful products, and it's easy to clean it, and it doesn't cause greenhouse effect, and it produces more energy per gram of fuel than petrol. So it's very efficient since there is no mechanical parts and there is no energy loss by heat. However, there's a plenty of limits of hydrogen fuel cells. First, high cost, and secondly, manufacturing of this kind of cells involves toxic byproducts because it involves the synthesis of platinum electrode, and this is highly pollutive. And we got a shortage of hydrogen because hydrogen can only produce cheaply by using fossil fuels, which means it's the same. It doesn't make difference between burning fossil fuels in the car engine and burning fossil fuel to produce hydrogen and then use it for car engines. And water will get freezed below 0 degrees, which means the battery won't work. So that's basically it. And we got additional one. It's more about electrolysis. We'll mainly discuss about the products of these. So first we are gonna say electrolysis of molten ionic compound. Electrolysis of molten I'll just write like that. We put cathode here and anode here. We all know that cations goes to cathode, so here we can get aluminum, and anions goes to anode. So we got oxygen gas here, and for magnesium bromide, we got magnesium at cathode, we got bromine gas at anode, and it's just as easy as year 3 mathematics. We just write it analogously. And now we are going to talk about those electrolysis of aqueous solution. Aqueous solution is pretty weird sometimes, so you have to memorize that for your exams and for further understanding. First is concentrated NaClAq. When we are talking about concentrated, it's always 1 molecule per decimal cubic. And we will write cathode here and anode here. First, we'll produce hydrogen gas at cathode because it has E standard of 0, and sodium plus has E plus below 0, which means H2 is more feasible to get produced, And at anode we got this. We got chlorine, since it's easier to get oxidized compared to oxygen in water. And concentrated copper sulfate. For copper sulfate, we got hydrogen as usual. And no, I'm sorry. We got copper instead of hydrogen, because copper has E standard of plus 0.80 and hydrogen got 0. So at anode we just got O2 and HO2. Recall the first reaction we're talking about in this lecture. Then we have concentrated sodium sulfate. At cathode, we still got this. It's the same reason as the first one. However, we'll get oxygen and water at anode instead of sulfur and oxygen. It's the same reason. It's just working with those E standard values. So maybe you can check in the back of our course book. There is a table of all E standard values for the most common reactions. So yeah, you'll see it later. We'll see it later. So that's not the trickiest part. And here we got a more tricky part. Products varies with concentration. A good example will be sodium chlorine. Alright, cathode here and anode here. When it's concentrated, hydrogen is produced at cathode, and at anode, chlorine is produced. When it's dilute, hydrogen is also produced at cathode. However, oxygen and water is produced at anode. But this is just an ideal condition when it's infinitely dilute. In practice, we'll get a mixture of oxygen and chlorine gas at anode, but if you just decrease the concentration of our dilute sodium chlorine solution, the proportion of oxygen will increase, and the proportion of chlorine gas we're getting is decreasing. So that's basically it for today, and I'm sorry for the incident about my chapter 19. I don't know what's happening about that. I don't know. And today I'm gonna teach myself chapter 21, and also record my lecturing. And we are starting lecturing about physical chemistry by Peter Atkins and organic chemistry by Clayton. Also, sometimes inorganic chemistry by Hoscroft. These three textbooks from university levels, I believe that's useful for both of us. And as Feynman said, if you want to learn something, if you want to master something, you should teach. So that's basically for today. Thank you, just in case anyone is watching, and see you. Bye.